Hello, and thank you for joining this presentation. My name is Srini Polavarapu. I am an engineering manager at Google, and I work on gRPC and service mesh technologies. So today I'll be presenting the exciting new development happening in gRPC in the area of service mesh technologies. So let's dive right into it. So I'll start by saying that gRPC is an awesome RPC framework. It is a high-performance open source framework with a ton of features, and it has very high industry adoption. It has a sophisticated networking stack that enables connection management, bidirectional streaming, flow control, and many more features. It is available in many languages and works great with protocol buffers. So all this makes gRPC an awesome framework for building microservices-based applications. Now, I will also say that service meshes are cool. As you know, microservices is the name of the game when you want to build scalable and highly available applications. So it is also known as service-oriented architecture, where a large application is divided into many small services that talk to each other over the network. So this provides great agility in developing and deploying parts of the application independently. So, but it comes with its own challenges and complexities, like how to discover services, how requests are load balanced to many replicas of a service, or how to secure the mesh or get insights into any issues or bottlenecks in the mesh. So these are common problems on which an application developer should not be wasting their time. And that's where a service mesh is very useful to solve these issues seamlessly. So as an example, check out Istio, which is an open source service mesh solution that is gaining a lot of popularity these days. Okay, but where does gRPC stand with respect to service mesh technologies? So out of the box, gRPC comes with a DNS resolver and a very simple pick first or round robin load balancing. So to do anything fancier, you have to write your own resolver and load balancing plugins. Right. The other option is to implement a controller that talks gRPC LB protocol, and we also call it look-aside load balancer. And all the smartness is built into this controller, which provides a flat list of endpoints for a given service to a gRPC client, which then does simple round-robin load balancing. Right? But unfortunately, there is no open source implementation available, so you will have to build your own such controller. So also, this protocol is very basic, and I would say it won't get you anywhere close to what a service mesh provides. So instead of evolving this protocol, it made sense to integrate with existing mesh technologies. So before I talk about that, let's see how a gRPC application is deployed in a service mesh today. In a commonly used model, and like any other application, the gRPC application is deployed along with a sidecar proxy that intercepts the request. The sidecar proxy gets service mesh policies from the control plane and apply them on the intercepted requests. So there is one sidecar proxy on each end of the connection, providing client-side and server-side mesh functionality. Right? So like any other application, a gRPC app client would do a DNS lookup of the service it is trying to connect to and open one connection to the virtual IP of the service. So as you can see, much of the sophistication in the gRPC stack is not being used. The sidecar proxy takes care of everything. Okay. With service mesh integration, a gRPC application would then directly talk to the service mesh control plane. Now, this looks similar to the look-aside gRPC LB solution that I showed earlier. But here, gRPC would be talking a much broader set of data plane APIs that enable supporting a large number of features available in a service mesh, right? So the key thing to note here is that we won't need a sidecar proxy in the middle. So as you can see in the previous diagram, there is a proxy on both sides of the connection, and here we don't have it. And that's why we are calling it proxy-less gRPC service mesh. So now the question is which service mesh to use. So it is not about picking a particular service mesh solution. The lessons we learned from gRPC LB protocol showed us that picking the right data plane API is the most important thing. So data plane APIs are used to exchange configuration data between the control plane and the data plane components like the proxies. In contrast, control plane APIs are used to program the control plane itself with information like what are the services in the mesh, what are the routing policies, and what is the current state of the mesh, like which services are up, which services are down, and so on. Right? So if we pick a widely used data plane API, then there will be good choice of control planes to use with your gRPC applications. So obviously the API has to be open and needs to have a strong community support. Also, it should fit the current gRPC architecture and align with our vision of no vendor lock-in, right? So XTS APIs fit the bill perfectly. And these APIs were developed for Envoy proxy, which is a very popular proxy used in many service mesh solutions like Istio. And because of that, XTS APIs have become a de facto standard for data plane APIs. And there is also an effort going on to evolve these APIs into universal data plane APIs for layer 4 to 7 data plane configuration. So I'll give you a quick overview of what XTS APIs are. So these are a collection of APIs to discover various resources in a service mesh. Hence the name XTS, where X stands for the type of resource, like a listener, a route, a cluster, or an endpoint. And there is also a lot more to XTS APIs than what I'm showing in this diagram, but I'll keep it simple here. So you have a virtual service in a service mesh, which is assigned a virtual IP and ports on which the service listens. And that is called a VIP. And when an application wants to send request to a service, it does DNS lookup and sends the request to the virtual IP, which is the VIP here. And this request is then intercepted by the sidecar proxy. So now the proxy needs to know about such virtual IPs in the service mesh so it can intercept such traffic and apply the policies of those services correctly, right? So that's where the listener discovery request is used to get the information about the virtual IPs. So now after intercepting the request, the proxy needs to know how to route the traffic and what policies to apply. So this information is obtained using the route discovery service. The config may include various rules like match on header values or a path, and then route to a particular cluster and apply a particular timeout or maybe insert a header, right? So once the proxy knows which cluster the request needs to be sent to, it then uses cluster discovery service to get cluster information, like what is the load balancing policies and what are the security policies, if any, right? So a cluster is basically the implementation of your service in the form of endpoints, right? So the cluster is made up of many endpoints that are the actual service instances. And these endpoints could be spread across different zones and regions which are known as localities in XDS terms. And that information is obtained via the endpoint discovery service. So as you can see, XDS APIs map very well to service mesh concepts that we are familiar with, right? So this is how the implementation of XDS in gRPC looks like. It is not as scary as it looks. It is a very modular design that maps the concepts of XDS APIs and integrates well with the gRPC client channel design. So there is a common XDS client implementation on the left that talks to the XDS server. So when you create a client channel in gRPC to connect to a service, you need to use the XDS scheme instead of the default DNS scheme. And this scheme tells the client channel that an XDS resolver needs to be created in order to resolve the service name. And then it sends an LDS request to resolve the name. So if the service exists, then it uses RDS to get the routing rules associated with that service. So a routing LB policy is then created to match the RPCs against the match rules, right? So based on the route action of the match rule, a traffic splitting policy or a single cluster load balancing policy is created. And as I said earlier, a cluster is made of endpoints in different localities. So the rest of the policies in the chain map to picking localities and then endpoints within those localities, right? So the common XDS client instance is responsible for talking to the XDS server and then give the discovery service data to the resolver and the load balancing plugins as needed. So the XDS client keeps a bidirectional gRPC stream open with the XDS server so that the server can push configuration and state changes in real time. So also, the gRPC client reports some metrics to the XDS server via the load reporting service, which is also part of the XDS APIs. So I will not go into more details here, but feel free to look up the design docs if you're interested. The links are provided in the last slide. Okay, so how do you enable XDS in your gRPC applications and go proxy-less? It is quite easy. Instead of using the default scheme when you create a channel, just use the new XDS scheme that tells the client channel to start an XDS resolver instead of a DNS resolver. Right? So in this example, you can see how XDS scheme is used to connect to a service called foo.myservice. Right? But then how does a gRPC application know which XDS server to talk to? So the address and the credentials of the XDS server needs to be provided via a bootstrap file in the local file system. And the location of the file is provided via an environment variable called gRPC XDS bootstrap. So the bootstrap can contain some other information such as a unique client ID, its locality, and any other data that is relevant to a particular XDS server implementation, such as a project number or a network number. Right? So, and that's it. And it is that simple. You can pick XDS or DNS resolver scheme on a per channel basis. So this means you can connect to some services via a proxy while connecting to some other services directly without a proxy. So this makes it easy to slowly migrate to proxy-less gRPC. Right? So what are the advantages of going proxy-less? Well, you get a better QPS and lower latency because you have two less proxies in the path, and one on the client side and one on the server side, right? And as the size of your service mesh grows, it becomes less efficient and scalable to have a proxy with each service. And proxies require some performance tuning to avoid impedance mismatch with the applications. So you could have a fast application bottlenecked by a slow proxy, right? So, and also a sidecar proxy requires a complex set of IP filter rules for intercepting traffic that are not needed in a proxyless deployment. And because the gRPC uses XTS to resolve a service name, you can even get away without configuring DNS entries for the services. Um, Also, proxies are additional binaries running in your service mesh. So there is an overhead of lifecycle management, like deploying, upgrading, health checking, and dealing with security issues. And that also makes it harder to deploy in VMs compared to pods. So with proxyless gRPC, you don't have these issues, which makes it easier to migrate your gRPC applications to a service mesh. And many service mesh solutions use XTS APIs. So there is a great value add if you are already invested in gRPC, or if you are thinking of adopting it. So this kind of proxyless model is used at many companies to build global scale services. So, so what are the downsides? So mature proxies like Envoy are very feature rich, and there is a large ecosystem of third-party filters and tools, especially in the area of observability. But we are actively working on adding more features in gRPC to close the feature gap. Right? So note that gRPC provides extensibility with interceptors, and there is a good open census and open tracing integration for observability. The other downside is to get XTS functionality, you will need to be able to upgrade gRPC version and rebuild your applications. So this is usually not an issue because developers building microservices-based applications typically have a good CI/CD infrastructure. Also, you can continue to use proxies with applications that cannot be upgraded because, as I talked earlier, it is easy to mix and match proxy and proxyless deployments. So the language support may be an issue for you. We already support C++, Java, Go, Python, PHP, Ruby, and C Sharp. Any gRPC implementation that wraps C core, for example, Python, gets XTS support for free. So such an implementation just needs to upgrade its core version. So, so where are we now? So in the past year, the gRPC team at Google has been working hard to make proxyless service mesh a reality, right? And I'm happy to say that we recently released 1.30 version that supports XTS protocol for service discovery and endpoint load balancing. We are also making good progress on adding route matching based on path and header values and splitting traffic to multiple clusters. There are several other features in the design phase, and we are migrating from XTS version 2 to version 3 sometime this year. So you can watch the progress on GitHub, and you are very welcome to contribute. So with this, I will switch to a demo of XTS functionality using gRPC Hello World application. I'll be using Google Cloud Managed Service Mesh Controller called Traffic Director that speaks XTS protocol. I will now do a quick demo using Traffic Director, which is a Google Cloud Managed Service Mesh Control plane. I have pre-configured a service called Hello World GCE in Traffic Director, and I have also configured a cluster for this service whose backend instances are in two regions. The top left two windows are instances in the central region, and the bottom two are instances in the west region. The client is in the central region, and it is using the XTS scheme to connect to the Hello World GCE service. Since Traffic Director also speaks XTS, the gRPC client is able to get the cluster and backend information from Traffic Director. And Traffic Director also provides global load balancing such that the requests are sent to the closest zone. you can see that the client is now sending requests to backends in the central zone, as that is the closest zone. Now I will stop the backends in the central zone, and you will see that the requests have immediately failed over to the backends in the west zone. The failover to another region is quite fast. This is because the client received assignments for all the zones, but with different priorities. The central zone was in the highest priority because it was closest to the client. And once it failed, the client immediately switched to the next priority zone. Now I will restart the service in the central zone, and we will see that in a few seconds, the request will fail back to the central zone. I have configured gRPC health check services here to check the health of the backends. The traffic director looks at the health of the backends before including them in the EDS response. So here now you can see that the requests have started coming back to the central zone. And now the client is not sending any request to the west zone. Okay. I would also like to quickly show the bootstrap file that this client is using. This is a sample bootstrap file. You can see that there is an address to the XDS server, and there is some node ID, which is basically a unique string that you can set to any value. And there is also a metadata, which the XDS server uses to identify the client, for example, the project number and the network name. And that concludes this demo. So that brings us to the end of this presentation. These are some useful links. If you have any questions or feedback, please use the link provided here to reach me. Thank you for listening, and we now open up for questions.